where do we go next? How do we take advantage of Fermat's theorem to help us identify where local maxes and mins occur? We're going to define a critical number. All right, so a critical number, an x value such that f prime of x equals 0 or f prime of x does not exist. Okay, so from Fermat's theorem, this makes sense, right? Local maxes and mins have to occur either where the derivative is 0 or does not exist, but we realized if we find all the critical numbers, if we find all the x values, we might be including x values that are not local maxes and mins. But this is the best we can do, and we're okay with this for now. So here it is in writing. Local maxes and mins occur only at critical numbers, yet critical numbers might include other x values that are not local maxes and mins. Okay, I've said it probably 5 or 6 times by now. So what are we going to do in this section? What do examples look like? The bread and butter, the primary examples we're doing are just to identify critical numbers. We're not even going to get to identifying local maxes and mins yet until the next section. We're just going to spend a lot of time just trying to find the critical numbers. This is big and it's going to build, so we really want to put a lot of attention on this. Okay, so here's our example, and from here it's just examples all the way with this concept. Okay, find the critical numbers. Let's start with a relatively easy one, about as easy as they get. F of x equals 1/3 x to the third minus x squared minus 15x. Just find the critical numbers. Okay, so the critical numbers, it's where the derivative either equals 0 or where the derivative does not exist. So in either case, obviously, we're going to need to know the derivative. So let's find the derivative first. And we got our polynomial, so that's nice, right? 1/3 x to the third, that 3 multiplies down and cancels the 1/3. So we just have x squared minus 2x minus 15. And okay. Now, we've got our two cases, right? Where does that derivative equal 0? What x values? Any x values where it does not exist. So you're going to see what's going on over here, but I'm just going to speak to where it equals 0, then we'll come back and explain the other one. All right, so we're going to begin. I'm just going to take my derivative function and set it equal to 0, solve for x. All right, we've got a quadratic equation there. Turns out this one can be factored nicely. X minus 5 times x plus 3. And hey, perfect. I have two x values, x equals 5 and x equals negative 3. They would cause the derivative to equal 0. So I'm going to stop here. I know that these are critical numbers. But before I finish the problem, I need to consider, hey, any values of x where the derivative does not exist? And, you know, my answer is there, right? But, you know, you kind of look back, where does that come from? Hey, are there any x values, like what do we mean by does not exist, right? Like what would that even look like? It's going to be things like just about everything we look at. It's going to be x values that cause you to be undefined. So the big way for that to happen is division by 0. All right, so is it possible, are there any x values that cause this f prime of x to be undefined? No. Right? We're never dividing by an x or anything where we have to think, oh, maybe like if x equals 0, you know. We're going to see an example like that next, because I definitely want to show you what that looks like. But here, now every x value is fine. There's no holes or jumps or anything like that. So x values where f prime of x is d and e, none. Which means these are the critical numbers. There's two of them, x equals 5, x equals negative 3. So we've got the answer here, but you know, if you kind of wanted to connect it to the bigger idea, if this function here has local maxes or mins, they occur at these points, at those x values. Now we don't know, if this is a local max or min, maybe this is a local max or min, maybe both of them are not local maxes or mins, right? Maybe it's like that x cubed kind of situation where there was a horizontal tangent line at the origin. We don't know, but we're off to a good start. If there are local maxes or mins, they would have to occur at 5 and -3 and nowhere else. All right, we're going to get deeper into that in the next section, as you know. Let's do a more difficult one. Still finding the critical numbers. We're going to go for it here. This will be good. G of x equals x to the 2/3 times x plus 3 quantity squared. Now, by the time we're done with this whole conversation, by the end of 4.3, you're going to have so much information about that graph, you'd be able to graph it without any technology. Get a really good idea of what it looks like. Isn't that crazy? That's pretty cool. I mean, even this one back here, to think, man, this will be like an easy one. Like, we'll be able to graph that without any technology or like just plugging in points or anything. Like, just with calculus. Pretty sweet. Okay. G of x equals x to the 2/3 x plus 3 squared. Well, we start with the derivative, right, to find the critical numbers. So this derivative, you may recognize, needs a product rule. Then the second half needs a chain rule. Okay, so here we go. Just got the whole thing laid out there. The product rule. Well, 2/3 x to the -1/3 times x plus 3 quantity squared plus x to the 2/3, and now that chain rule times 2 x plus 3 to the first times the derivative of the inside. Well, that would just be 1. Okay, I cannot overstate what I'm about to say. Now that we are doing applications of derivatives, you've got to get that derivative spot on. From this point forward in the course, we are assuming that you are masters of derivatives. Anything that gets thrown at you, you can take a derivative, no problem, no mistakes. We have to assume that for where it's going. So, for example, if you miss the fact that that's a product rule, in the two parts, if that happens on a quiz or your final, that's going to be a massive hit to the points. I mean, you'll hardly get any points for any of the work you do from then on in a question like this. That's not me being harsh. That's just the nature and the unforgiveness of calculus from this point forward. You have to get that derivative right. It's kind of like, when you're learning algebra, you have to know how to add and subtract and multiply and divide. Right? You can't mess that up. Small mistakes happen, of course. But like missing the fact that this is a product rule would be a massive, massive mistake. And that you can't let that happen. So take your time with the derivative. Don't rush the derivative. It's not a short problem. So there's a tendency to want to, just get to it. Like, take the derivative, move on, let's get through it. Don't do that. Slow down. You've got to get that derivative perfect. Okay. Then what? So because we're doing more than just take a derivative now, we want to write this. I think you could argue in a simplified way, but I think we want it to look a lot cleaner. It's not so much simplifying just the way that these terms are, but let's make it look a lot cleaner. Okay. So the focus is here, and I've got this negative exponent. I'm going to write this as a fraction. Okay. Here's what I want g prime of x to look like. So that 2 here can stay in the numerator, so can the x plus 3 quantity squared. I'm going to take this 3 to the denominator, as well as x to the 1/3. this is going to be much easier to work with as the problem moves forward. And then over here, well, you know, the first power is not necessary, the times 1. Let's put the 2 out. There's really not as much to do there. 2x to the 2/3 x plus 3. Okay. Now that we have the derivative and it's in this nice and neat, you know, it's presented nice and neat, what are we going to do? Well, we got to think about the 2 possibilities, starting with, when does that derivative, what x values, will that equal 0? So I'm just going to take my derivative, set it equal to 0. Okay, 2x plus 3 quantity squared over 3x to the 1/3 plus 2x to the 2/3 times x plus 3 equals 0. Now this is intimidating, no doubt about it. But because we wrote this first part in a much more accessible form, we're actually just one step away from this equation looking a whole lot better. When you look at this thing, like, what gives you trouble? What troubles your heart as you look at that equation and think about solving it? And think, well, one thing that gives me trouble is this denominator. I don't like that denominator there. I also don't like this other fractional exponent, you might be thinking. Those 2 things are troublesome. Hey, we're going to get rid of both of them in one shot. Let's multiply both sides by this denominator. Multiply both sides by 3x to the 1/3. In that case, it'll cancel here, but it's also going to clean this up really well. And since we are multiplying by 0, hey, it's going to stay 0. So if we multiply all 3 parts by 3x to the 1/3, what happens? Looks a whole lot better. Okay, so 3x to the 1/3 times this, well, it cancels, so that's just gone. 3x to the 1/3 times 2x to the 2/3. Well, that would be 6. And then what's x to the 2/3 times x to the 1/3? You add the exponents. So that would be x to the 1st. So this just becomes 6x, x plus 3, and then, of course, you multiply it by 0, and it stays 0. Wow! That's pretty cool. Now, the truth is, I like to write it in this fractional form. You could have left it as 2/3 x to the negative 1/3, you know, the way we first took the derivative. If you can recognize this, you know, that it would still cancel out, I kind of like it as that denominator. That makes it a lot more clear to my mind. Hey, multiply by that denominator and it'll cancel. And then it happens to clean up this one perfectly. Like, yes. Hey, was that a coincidence? Was that just, is this just a nice problem I chose to present to you guys, and the chances of this happening again in like your homework or a quiz or something are like minuscule? No. No, this happens all the time. It's predictable this would happen, in fact. Why? Because the way derivatives work, right? So when we took the derivative of x to the 2/3, we subtracted 1. We got x to the negative 1/3. It's no surprise that these would add up to 1. Because the way, the power rule. Okay. I think that's enough. Let's go on. Can we solve for x? Now, okay, slow down. It's going to be really tempting to like multiply everything out. Foil this, distribute this, right? In this case, that would work perfectly well. But there is a faster way. What's the faster way? Just think of this as like 2 terms. I've got this term here and this term here. And I want to factor. It's equal to 0. Could I factor between these two? What do these two have in common? Okay. Don't multiply it all out. Well, let's see. What do they have in common? A 2 and an x plus 3. So let's factor out 2x plus 3. And what does that leave us with? Well, this one has another x plus 3. And this one, 2 becoming 6x, needs plus 3x. Why would I multiply all this out just to refactor? If I can factor now, just factor now. All right, boom, boom. And look at this. Let's simplify what's in these brackets. 2x plus 3 and 4x plus 3. Hey, I can get my solutions of x right here. The x plus 3, of course, gives me x equals negative 3. The 4x plus 3, well, if it's equal to 0, subtract 3, divide by 4, x equals negative 3/4. Yes! Be wise in your solving. Don't just blow everything up. You know, you could still get it. In other cases, it might be more difficult, right? Here we had a square and a first power. But what if that was like, what if it was like a fifth power and a fourth power? You don't want to multiply all that out, but you could still factor. Okay. And get the answer just as quickly as I did here. So it's not even about like correct algebra. It's even more, it's like, you know, really thoughtful, tactful algebra. Okay. So these will be two critical numbers. We will also need to know where g prime of x does not exist, and here we're going to get one. Let me just copy that derivative over again so it's nice and clear. It's all on the screen. There's our derivative. And you look at that and you think, okay, just looking at it, we don't have to solve anything. Are there any values of x that would cause this g prime to be DNE? Does not exist, or maybe a better word is undefined. Are there any x values that would cause this derivative to be undefined? Yes, we now have a denominator. If 3x to the 1/3 equals 0, then that's going to be undefined. Well, if 3x to the 1/3 equals 0, then that, of course, means x equals 0. And I've got my note there. X equals 0 causes division by 0. So this is a critical number. It's a possible local max or local min. And now we have them all. We've got these three. There, we got three critical numbers, I should say. X equals negative 3, x equals negative 3 over 4, and x equals 0. Now what you might want to do at the end of a question like this one, go back and graph the original g of x and see what's happening at these x values. Are they local maxes or mins? Is there a cusp? Is it nice and rounded? You know, maybe it's nothing. Maybe it's just some point in the middle. You know, that's it for this video. I think I'm going to do a Desmos on this because I would do it in class. I'd show you the graph and we just kind of like look back at it. But that's it for this video. We're going to talk about absolute maxes and mins next.